So there's a video going around right now claiming China just switched on a nuclear reactor that runs on sand. Just sand. Scoop it off a beach, drop it in, get power out the other end. And it sounds completely insane, which is exactly why it's gotten hundreds of millions of views. Here's the thing, it's not true. Not the way that video says it, but, and stay with me here, the real story hiding underneath that lie is actually more interesting than the myth. Because China did build something genuinely strange in the middle of the Gobi Desert. It just isn't sand-powered. It's something else. Something that got invented in America in the 1960s, got shut down by the American government in 1976, sat on a shelf for almost 50 years, and then China picked it back up and made it work. By the end of this video, you'll understand exactly what that sand actually is. How this reactor is built so differently from every nuclear plant you've heard of that it can't melt down the same way. And why the country that invented this idea walked away from it, while the country that copied the homework is now years ahead. Quick honest note before we go further. Nuclear energy is a genuinely technical and sometimes politically charged subject. Nothing here is anti-nuclear or pro-nuclear cheerleading. It's just what the engineering and the research papers actually say, and I'll flag clearly wherever something is still uncertain or unproven at scale. Okay, let's start with the sand. The sand in that viral claim is real, it's just badly described. It's a mineral called monazite, and sometimes a mineral called thorite. Both of these are just ordinary-looking sand you'd find in certain riverbeds and beach deposits, mostly in places like India, China, and parts of Australia and Brazil. And baked into that sand, mixed in with other minerals, is an element called thorium. Thorium is where the confusion starts. Thorium is not fuel, not directly. You cannot mine it, refine it a bit, and toss it into a reactor to make power, the way you basically can with enriched uranium. Thorium on its own just sits there. It's what's called fertile, not fissile. Those two words sound almost identical, but they mean completely different things. Fissile means an atom that will split apart and release energy if a neutron hits it. That's what uranium-235 does, that's what plutonium does. Fertile means an atom that, if you hit it with a neutron, doesn't split. It just quietly absorbs the neutron and turns into something else. Thorium absorbs a neutron and, after a couple of steps, turns into a new element called uranium-233. And U-233 is fissile. That's the actual fuel. Thorium is just the raw material you cook it from inside a working reactor using neutrons the reactor itself is already making. So the honest one-sentence version is this. The sand is a source of a fertile precursor, not a fuel, and it has to be converted inside a live reactor into the thing that actually burns. That's a very different claim than runs on sand. But it's still a real and important idea because thorium is roughly 3 to 4 times more abundant in the Earth's crust than uranium is. There's a lot of it sitting around, mostly ignored, because for 70 years, the entire global nuclear industry built itself around uranium instead. Which brings us to why. Why uranium and not this? For that, we have to go back to Tennessee in 1965. There was an American physicist named Alvin Weinberg running Oak Ridge National Laboratory, and his team built something called the Molten Salt Reactor Experiment, the MSRE. It's the direct ancestor of what China is running today. Weinberg's reactor didn't use solid fuel rods like every nuclear plant you've probably pictured. Instead, he dissolved the nuclear fuel directly into a liquid. A molten salt, mostly fluoride salts, heated until they flowed like hot water. The fuel wasn't a solid chunk sitting in a tube. It was mixed all the way through the liquid itself, running through the whole reactor loop. For 4 years, from 1965 to 1969, that experimental reactor ran. It worked. It proved liquid fuel reactors were not just a theory. And then in 1976, the US government cut the funding and shut the whole program down. Not because it failed, because of politics, budget priorities, and the fact that the entire American nuclear weapons and nuclear power infrastructure was already built around solid uranium fuel rods, and switching lanes would have meant starting over. Weinberg himself was pushed out of Oak Ridge partly over disagreements about reactor safety priorities. The molten salt idea didn't die because it was disproven. It died because nobody with power wanted to keep paying for it. And it sat there. In old Oak Ridge reports, gathering dust for almost 50 years. Then, starting around 2011, the Chinese Academy of Sciences launched a program to specifically dig that research back up. And in 2023, in Wuwei, in Gansu province, out in the Gobi Desert, they switched on something called TMSR-LF1, thorium molten salt reactor, liquid fuel generation 1. It reached criticality in 2023 and successfully ran on a thorium-derived fuel cycle in later tests. It's small, so about 2 megawatts, which is a tiny experimental test reactor, nowhere near a commercial power plant, roughly enough to power a couple thousand homes, not a city. But small is the point right now. It's a proof of concept. The same way the 1965 Oak Ridge reactor was a proof of concept. China built the successor experiment that America walked away from. Now let's actually get into how this thing works, because this is where it gets genuinely clever. Picture 2 ways to eat sugar. You can eat a sugar cube, solid, all in one lump. Or you can stir sugar into a glass of water until it's completely dissolved, so it's not a lump anymore. It's spread evenly through the whole liquid. A normal nuclear reactor, the kind in almost every nuclear plant on Earth, is the sugar cube. The fuel is packed into solid rods, solid pellets, stacked inside metal tubes. TMSR-LF1 is the dissolved sugar. The nuclear fuel is chemically dissolved directly into the molten fluoride salt, so fuel and coolant are the same liquid, flowing together through the whole reactor as one. Why does that matter so much? 2 huge reasons. Reason 1, temperature and pressure. Normal reactors use water as a coolant, and to keep water liquid at reactor operating temperatures, you have to pressurize it enormously. That's why containment structures are built like fortresses, because you're containing water that desperately wants to flash into steam. TMSR-LF1 runs at around 650 degrees Celsius, but at basically atmospheric pressure, because molten salt stays liquid at those temperatures without needing to be crushed under pressure. No high-pressure steam system means no steam explosion risk, which is the mechanism behind some of the worst reactor accidents in history. Reason 2, and this is the big one, the freeze plug. At the bottom of the reactor, there's a small plug of frozen salt, kept solid by a fan blowing cool air on it. If the reactor overheats for any reason, equipment failure, power loss, anything, that fan stops or the salt around the plug gets too hot, and the plug melts on its own with no human, no computer, no backup generator required. The instant it melts, gravity takes over. The entire liquid fuel drains straight down into a dump tank shaped and spaced specifically so the fuel can't sustain a chain reaction once it's down there. The reaction simply stops. Passively. Because physics did it. Not because a system responded correctly under pressure. That's the fundamental difference from a meltdown. A meltdown happens when solid fuel rods get so hot they lose their structure and slump into an uncontrollable molten mass, while still trying to be cooled by water that may be failing to circulate. In this design, the fuel is already liquid, on purpose all the time. So instead of an uncontrolled meltdown, an overheating event triggers a controlled drain into a tank built to shut the reaction down. It's not that this reactor is immune to every possible failure. It's that its worst-case failure mode looks completely different and much less catastrophic than the worst-case failure mode of a Chernobyl or a Fukushima. So now let's talk about why any of this is actually worth caring about, beyond just being a cool engineering trick. First, abundance. Thorium is 3 to 4 times more common in the Earth's crust than uranium, and countries like India and China are sitting on huge deposits of it, often as a byproduct of mining for other rare earth elements they're already extracting for magnets and electronics. That's not a small detail. It means thorium fuel could plug directly into supply chains that already exist. Second, weapons proliferation. This is genuinely one of the more underrated points here. When thorium converts into U-233 inside the reactor, it comes packaged with a contaminant called U-232, which decays and produces strong gamma radiation. That radiation makes the material extremely difficult and dangerous to handle covertly. You basically can't sneak it out and build a weapon with it without heavy shielding and serious detection risk. Researchers call this self-protecting. It doesn't make weapons use impossible, but it raises the bar dramatically compared to some other fuel cycles, which is a real advantage in a world worried about nuclear material ending up somewhere it shouldn't. Third, and maybe the most concrete number in this whole video, waste. Conventional uranium reactor waste contains long-lived transuranic elements, plutonium and friends, that stay dangerously radioactive for over 10,000 years. That's the number that makes long-term nuclear waste storage such a nightmare. Planning for timelines longer than recorded human history. Thorium fuel cycles produce far smaller amounts of those transuranic elements, and the resulting waste is projected to fall to safer levels in roughly 300 years instead. 300 years is a number a government can actually plan around. 10,000 years basically isn't. Now, geopolitics briefly, because it matters. The US invented this concept, ran the original experiment successfully, then defunded it in 1976 and never built a follow-up at any real scale. Today, American thorium and molten salt efforts, companies like Kairos Power and Flybe Energy, alongside advanced reactor players like NuScale working on different but related next-gen designs, are real, serious, and still pre-commercial, mostly in testing, licensing, or early construction phases. China, meanwhile, already has an operating experimental reactor, an active roadmap, and a national strategy that ties directly into its dominance of rare earth mineral processing. This isn't a case of China inventing something from nothing. It's a case of China finishing a project the country that invented it walked away from, and getting there years, maybe decades ahead. Now for the honest part, because a clear-headed explainer doesn't get to skip this. This is genuinely hard engineering, and there are real unsolved problems. Hot fluoride salts are corrosive, and finding pipe and vessel materials that can survive decades of exposure at 650 degrees without degrading is an ongoing materials science challenge, not a solved one. Because the fuel is a liquid mixed through the whole system, you eventually need some form of online reprocessing, chemically separating and refreshing the fuel while the reactor keeps running. And doing that continuously, safely, and efficiently at scale has never been done commercially anywhere. And these reactors produce tritium, a radioactive form of hydrogen that's notoriously difficult to fully contain, which is still an active area of engineering research. And here's the timeline reality. China's own published roadmap targets commercial-scale thorium molten salt reactors only by the mid-2030s at the earliest. TMSR-LF1 is a 2-megawatt experimental test reactor, not a power plant, not something plugged into anyone's electric grid yet. This is a proof of concept succeeding, not a finished technology arriving. So here's the grounded verdict. The viral claim that China built a reactor that runs on sand is technically wrong. Thorium sand is not fuel. It's a fertile raw material that has to be converted inside a working reactor into something else that actually burns. But underneath that sloppy clickbait framing is a real and quietly important story. An idea born in 1965, killed by politics in 1976, and resurrected in the Gobi Desert in 2023. A reactor that can't melt down the way we're used to, that runs on one of the most abundant elements on Earth, that resists weapons proliferation almost by accident, and that leaves behind a waste problem measured in centuries instead of millennia. It's not ready. It's not scaled. It's not going to power your house next year, but it is. Without the sand-flavored spin, one of the more genuinely underreported shifts happening in energy right now, and it's worth understanding exactly as it is, not as a headline made it sound.